Next up is Edward Hutter from the University of Illinois at Urbana-Champaign. His field is computer science. His advisor is Edgar Solomonic, and he's done his practicum at Oak Ridge.
So unlike previous talks, this talk will focus solely on high-performance computing. This fellowship has allowed me to pursue multiple directions within HPC, including designing algorithms for dense matrix factorizations that minimize communication across nodes, designing techniques to accelerate automatic performance tuning at scale, as well as designing methods for accurate high-dimensional performance modeling. And this talk will focus primarily on this latter effort, not just because it's my most recent work, but because I think it's of immediate interest to many in this audience who seek better models for the performance of their scientific applications. Now, one of the key trends that presents challenges for software optimization is the increasing diversity and heterogeneity among architectures. Ideally, software should be optimized for any architecture, and to achieve performance portability without writing an excessive amount of code, software is becoming increasingly parameterized, meaning that the performance of scientific applications is very much dependent not just on input parameters, but on tuning parameters and architectural parameters as well. And so design spaces for methods and algorithms are increasing in dimension, and performance across these spaces is becoming increasingly difficult to model. And so this talk will introduce new methods for modeling these black box performance functions, which are largely devoid of structure, and we'll do so by sampling from design spaces, executing those configurations, and then constructing models to fit the data. Now, to keep everybody interested, I wanted to introduce some results first. And the takeaway from this slide is that our methods are more accurate than available machine learning methods, independent of model size. So our methods are on the left, the dark blue, and we compare against extremely randomized trees, Gaussian process regression, sparse grid regression, spline regression for two applications here. QR factorization takes 7 parameters, and a fast multiple method takes 5. And I want to mention that the most accurate machine learning method, so randomized tree regression, those models take upwards of 1,000 times more memory than our methods. Right, so I think that the problem that I'm most interested in is algorithm selection. And that problem, it asks, given a set of input parameters that define a problem, what are the tuning parameters and architectural parameters that minimize time to solution? And this is a very old problem, and it's been very well studied. And it's becoming increasingly important because optimal tuning parameter selection is critical for effective utilization of emerging architectures. And so scientific applications, right, as I mentioned, are not just dependent on a choice of library or architecture, but on tuning and architectural parameters as well. So for example, block sizes can control the amount of communication up and down the cache hierarchy, as well as the arithmetic intensity within loop nests. Pipeline depth can control the amount of task parallelism within applications. And processor grids can control or feature trade-offs in memory footprint, communication across the network, number of messages sent, et cetera. Architectural parameters, right, can include thread count per core, thread count across nodes, processes per node, even things such as core frequency, which has been studied very recently. The area that has perhaps seen the most intensive optimization effort, I would say, is dense linear algebra. For example, the LINPACK benchmark features over 12 tuning parameters and is used to judge the efficacy of architectural designs. So this talk will use distributed memory QR factorization to introduce our methods, and as many will be aware, QR factorization takes an m by n matrix A and factors it into a product of an orthogonal matrix of size m by n and an upper triangular matrix of size n by n. And so I list a few select libraries that implement this routine, and I want to mention that our library Capital, which I wrote, is the only to this day that achieves asymptotically minimal communication along the critical execution path. And so that's the quantity in green, and I want to give some intuition behind that. The work per core for this routine is mn squared over p, and the surface area of the volume of computation, if you think of mn squared over p as a volume of computation, the surface area of that is this quantity to the 2/3, and that reflects the minimal amount of communication to compute the volume of computation. And I should mention that there is a well-known trade-off between number of words and number of messages sent along the critical path. So let's start simple. Let's break down the parallel execution time, which is t-exec, into time spent computing floating point operations with register resident data, time spent communicating bytes of data and injecting them into the network and across levels of the cache hierarchy, and time spent sending messages. So 0-byte messages, that's the time, that's the synchronization time. And we can bound T-exec. The lower bound reflects compute bound or bandwidth bound behavior in which 2 of the 3 time components are overlapped, and the upper bound reflects an additive sum, so no overlap. And if we construct linear regression models that reflect the number of flops, the number of words, the number of messages, the model on the left reflects the lower bound, the model on the right reflects the upper bound for QR factorization. What we find, and C0, C1, C2 are solved parameters. What we find is that if we if we vary the number of rows and number of columns in both plots here, dark red represents very high relative error. These models are not, they do not suffice to accurately model performance. So we want to improve upon these models, and we want to systematically transform these linear regression models. So blue symbols reflect solved parameters, and black text reflects input parameters. And we want to systematically transform this linear regression model into a summation of products of latent functions. So at the very bottom, we have this summation of functions, UR, VR, and WR. We do not know what those are, so we want to learn these cost-based functions for each parameter. And on the left, we have the configuration space, which reflects the input size and number of processes used. And what we find is that if we discretize these functions, we arrive at a well-known problem, and that is factoring a tensor, a low-rank tensor factorization. And I want to mention that so finding the exact or approximate tensor rank of a tensor is an NP-hard problem. So instead, we want to ask the question, can low-rank tensor factorizations model performance across high-dimensional configuration spaces? And so CP tensor decompositions, so canonical pilotic tensor decompositions, use a summation of tensor products. And U, V, and W reflect solved parameters. So we have factor matrices, U, V, and W, and I wanted to make the connection between the linear regression model. They can be equivalent. So if we store elements for U, V, and W as shown, that exactly represents the linear regression model, although when we solve for these factor matrices, we want to attain a more accurate model. And so the assumption thus far is that we have a dense tensor of executed configurations, and that's obviously not tractable in any way. So what we want to slightly perturb the problem and say, okay, if we start with a very sparse tensor, such as what's on the left, can we attain a model that not only accurately models executed or observed tensor entries, but also accurately models unobserved entries? And so this also is a well-known problem. This is the tensor completion problem. So starting with a training set, omega, as shown, I give the objective that we want to minimize over the elements in the factor matrices U, V, and W. So we want to minimize the training error, which is the Frobenius norm error on observed entries, and to avoid overfitting to training data, we include regularization terms as well. Okay, so but the objective just shown will not achieve high relative accuracy for performance data. And so we log transform the execution times, as well as sometimes log transform the model form as well. So we have a least squares loss and a generalized least squares loss. And to optimize these models, we use the alternating least squares framework, which fixes all model parameters in all but one factor matrix and performs sequences of either quadratic optimization problems or sequences of convex optimization problems. So optimize U, V, and W, and just cycle through those until we attain a decent accuracy. And so one other assumption is that we're able to place a tensor element for every configuration, and that's also not scalable. So instead, we partition configuration spaces, and all training samples that are mapped within a subspace. So we perform a sample mean on those execution times, and that reflects the tensor element. And then come inference time, we perform multilinear interpolation of the completed tensor elements. And I'm going to skip. So these are ablation studies, but I'm going to come back to these in case there's any questions, because I wanted to go to the results. So we already saw some results, and now these results differ because I vary the model size. So we look at the most accurate machine learning method that I tried, which is extremely randomized trees, and then also regression splines. And I should mention that the purple dot reflects the linear regression model we solved earlier, which has a very high relative error. The black line reflects our method, and what we see is that our methods are significantly more accurate relative to the model size, and also even for matrix multiplication, so Intel MKL's gem routine. We attain a relative error around 1%, and the extremely randomized trees sees upward like maybe 5%, so a factor of 5 difference. And on the right, we have QR factorization with 7 parameters, and we see upwards of a 4-time improvement in relative error. And to tie this into the DOE, we also modeled 2 DOE mini apps, Snap and KryptKey. Snap and KryptKey. And so those are the plots on the center and the right. And again, compared to extremely randomized trees, our methods are much more accurate. Okay, so as mentioned, I also studied many other problems throughout this fellowship. I studied communication avoiding algorithms for QR factorization and the corresponding software library Capital, which was published a few years back. I also studied methods for accelerating automatic performance tuning at scale, which was published last year. And obviously, I just mentioned our current work. We are looking to integrate this work into automatic performance tuning using tensor factorization models. And I would like to thank my advisor, Edgar. I would like to thank the DOE, obviously, for funding this research, Blue Waters and Stampede 2 for providing compute resources. And I'll take any questions, and also, I guess we'll go back to, since there is a bit of time, these ablation studies to provide more intuition behind these methods. So higher tensor rank, for example, tensor rank 8 versus tensor rank 2 on the plot to the left. We need about a tensor rank of 8 to achieve the baseline error, which is interpolation error of a dense tensor. But we do not need a higher tensor rank than that. If we needed a tensor rank of like 100, these methods would not be scalable.
All right, let's thank our speaker.